Alrighty, so today we're going to be talking about building an IoT backend using the X platform. So here's a bit of a summary of what's to come. So first, what do we mean when we talk about IoT and some of the challenges presented by systems in that domain? Next, we'll take a look at Neve's X platform and why it's well suited to many of those challenges. Lastly, we'll look at a simple working example of what an IoT data collection backend built on the X platform might look like. So it's a bit of an architecture walkthrough, some code, and a quick demo to show some latency numbers. All right, so what is the Internet of Things? I expect most folks on this call might be familiar with IoT, and this slide pretty much speaks for itself, but the Internet of Things basically refers to everyday physical devices connected to a network. So my favorite example is the IoT fridge that maybe has a sensor hooked up to detect when you're getting low on milk and shoots you an email at work. But if you want to think of a little something on the larger end of the scale, perhaps a more interesting example might be where our devices are some sort of widely deployed consumer electronics product, like maybe a Nest thermostat or something like that. And maybe you sold your Internet Aware widget to a few million customers across the globe, and you've got all these devices reporting in with sensor data multiple times per minute, and you want to collect all that data and put it in a chart on a dashboard somewhere, personalized for each customer, or something like that. So what are some of the challenges that we might expect trying to tackle that sort of load? So first of all, our backend needs to be capable of processing lots of messages from our IoT devices. In fact, processing events from IoT devices, applying some business logic and maybe storing the results or the raw data somewhere is virtually all we're doing. On top of that, it's sort of a given that we want to process messages from those devices as fast as possible. The faster we can process these messages, the faster we can get useful data into our customers' hands. But on top of that, if our system performs well, we can make better use of the hardware available to us, and so we're more cost-effective overall. You often hear the argument that hardware is cheap, but more than once I've seen teams in some enterprise environments get, like 3 servers after asking for 9 because of CapEx constraints or whatever. So all other things being equal, moving more messages per second with less hardware is never a bad thing. On the scalability front, so say today, maybe we're dealing with 50K events per second at peak. In a month, it could be double that. In a year, maybe 10x. So obviously, we want to be able to scale out our systems to deal with those sometimes exponential increases in throughput. On the reliability front, some messages are super important. We absolutely cannot lose them. So for a terrible example, consider an alert from an IoT-enabled pacemaker. You don't want to miss that thing. Likewise, we want to minimize downtime and need some sort of HA configuration to make sure that everything keeps running smoothly in the event of some sort of failure. And what we mean by agility here is the ability for your systems to easily evolve and change over time, and that's in spite of changes to business and non-functional requirements. So it's kind of maintainability, but sort of changeability, fungibility. Can our system evolve to meet our needs as time goes on? So now that we've covered that, those aspects of IoT that are important, let's move on to talk a bit about the X platform and how we can meet those challenges head on. So in a nutshell, this is what X is all about. It's a memory-oriented platform for enterprise Java applications. And what's really great about X is its emphasis on hiding away all of the non-functional concerns so that you can just focus on writing the business logic that's relevant to your application. And what that means is that when you're writing X applications, you don't need to worry about dealing with the fact that you're sending messages over JMS. You don't need to implement special logic to ensure guaranteed delivery or to write the replication logic to ensure HA in the event of an unexpected power outage. All those details are sort of squirreled away in configuration. So when it comes to your business logic, you can usually just say, hey, I want to do this without worrying about the how of how that happens under the hood. And everything sort of just works. So as I was just saying, all you really need to worry about is writing your Java business logic, and this slide is trying to emphasize that from an architectural perspective. So first of all, your X applications are made up of some message handlers, which you can see over here, and some state. The message handlers are basically just Java methods that service inbound messages and maybe manipulate some state in response to those messages. And when you modify the state here, you're really just calling getters and setters on POJOs. So all you're doing is really just modifying objects in memory. But even though you're just modifying objects in memory, X can be configured to transparently replicate that state to a hot backup. So that's sort of your HA story. Your code doesn't need to worry so much about the how of what's going on there. It's just manipulating POJOs, which is nice and simple, obviously. So we've got inbound messages coming in from the messaging fabric. X will deserialize those messages into POJOs for you. X natively speaks in efficient binary format in the wire. Then X will determine which message handler needs to be invoked to process that message. It'll usually look at the type of message that's coming in order to do that. We'll take a closer look at how that happens in a minute. Remember, the message handler is your business logic. It's the code that you write as a developer using the X platform. They're just plain old Java methods with a little annotation at the top of them. So maybe your message handler modifies some state, and then once it's done that, it may need to send some outbound messages to some other application to tell it to do something in response. Again, these messages are just POJOs, and your message handling logic doesn't need to know anything about the underlying transport. So Kafka, JMS, who cares? All you need to say in your code is please send this message. Okay, so if the previous slide was sort of a bird's eye view of an X app, this is sort of a little bit more detail. Now we're starting to look inside, the source code for an application, what it sort of looks like. As I mentioned, we have messages, state, and message handlers. We model our state and message schemas using XML. We run a code generator at build time to convert that XML into POJOs. Then we write our Java code to process those messages, manipulate our state, and maybe send some outbound messages. So here we've modeled a message called myInboundMessage and a state object called myAppState. We can ask X to inject them into our message handler method by just adding them as parameters down here. Oh, sorry, I've lost my place. So up here we've got our event handler annotation. You'll notice the method is called onMessage, but the name of the method doesn't really matter all that much. It's really this annotation up here and the type of this message that X sort of uses to determine, if you think back to when we were receiving inbound messages, we'll look at the type of that message and then dispatch to an event handler based on the type of the message. So if you've got a sharp eye, you'll see that there's no synchronization or locking code in here. That's because message handlers run single-threaded. So if you're familiar with other Java technologies like servlets and stuff like that, it's not unusual to have multiple threads competing for resources. But the thing is, modern server-class CPUs are really fast, and because we're building on X, we're talking about an in-memory system here. So all your message handler does is manipulate objects in RAM. We're not blocking up threads, waiting for database queries to finish, or for disk seeks, or whatever. You can really push your hardware to its limit. And if you do need more than one thread, that's trivial too. But even then, the single-threaded programming model of the message handlers still doesn't really change. So now that we've looked at the details of what's involved in building an X app, I just want to quickly go over some other stuff you basically get for free when you use X. So X was designed to operate in a multi-agent environment, meaning you typically have two or more applications collaborating with one another rather than a big old monolith. It's sort of a system design consideration, whether you run all your apps across multiple threads within a single JVM, or if you want to get a bit trickier and deploy to multiple hosts or separate JVMs on the same host or whatever. The neat part is your Java code doesn't really need to care. It's just a few changes to some config files to change those the deployment details. We sort of touched on it in the past few slides, but in case it's not clear, X apps are in memory, so you're just fiddling with POJOs in RAM, not waiting for slow database queries to come back or anything like that. Again, we touched on it before, but we're fault tolerant, and we support automatic transparent replication backups, redelivery of unactive messages, and all that sort of good stuff. Again, your business logic doesn't need to care about any of this. It all happens under the hood. You just write your message handler, and those messages come through, and you process them. And you don't worry about the other details. On the scalability front, if you're dealing with extremely high throughput, you can deploy multiple instances of the same app across multiple threads or JVMs. Those JVMs can be running on multiple hosts, and shouting by some special key is easy if you need to do something like that. X apps are fast. We typically measure response times in microseconds. You'll see that a little later we're doing just that in this example application. We'll show you a bit of a demo. X itself generates very little garbage. With some discipline and careful configuration, you can ensure that both X and your message handlers allocate zero garbage. Now, I hope you got the gist of it in my previous slides, but X applications are very easy to write. You don't need to worry about threads or locking or any of that. You just write your business logic in some message handlers, fiddle with some POJOs, and X takes care of the hard stuff for you. So why does X make sense for IoT? I'm just quickly revisiting this slide from earlier, so hopefully some of this is sort of self-evident after all of my rambling so far about X, but X takes care of dealing with the low-level details, and you can focus on message processing. It's designed for event-driven systems and streaming lots of events. On the speed front, response times are typically measured in microseconds. On the scalability front, again, as throughput increases, you can scale your app vertically across multiple threads or JVMs on the same machine, or horizontally across any number of machines with just a few lines of config. With some careful planning, your business logic doesn't even need to necessarily change as you scale up. As for reliability, I mentioned we offer HA via transparent replication. We also offer things like guaranteed exactly once message delivery for critical messages that absolutely must reach their destination. And more than anything else, I'd say the agility aspect is what we're all about. X does its darndest to ensure that when it comes time to actually writing your application, all you need to think about is the business logic in your message handlers. Message handlers are single thread and thus easy to write, debug, and analyze. So over here, you can see this no architectural compromise thing. What we're trying to get at is by choosing X as a basis for your IoT backend, you don't have to sacrifice scalability for reliability or agility, or to choose between a high-performance system and one that's easy to understand and maintain. From the perspective of engineering effort, there's really very little difference between the X system that runs standalone on a single JVM and the X system that's clustered across multiple hosts. It really is just a few lines of config. Okay, so onto the example app. Today we're going to be looking at the backend for a fleet management system. So we've got some vehicles driving around, and they have some special IoT device welded into their frame or whatever. That's reporting their location up to our IoT backend. And that system needs to let us know if the vehicle veers outside some predetermined route. To give you an idea of why somebody might want an application like this, I was reading about a company that collects leftover scrap metal from other manufacturing companies to recycle. Before they adopted a fleet management system, the company had a theft problem. So, a driver would get into a truck in the morning, go pick up all of his scrap metal, and then disappear into the sunset with the truck and all the scrap metal. And obviously, that's an expensive problem to have. And so their fleet management system lets them keep track of their drivers and where their trucks are, and obviously saves them a lot of money over time. Anyway, today we're going to look at how you might go about building a system like this, in particular focusing on how we can build out a back-end data collection system using the X platform. So just reiterating our requirements a little bit here. So we have a bunch of vehicles driving around. Each vehicle has a predetermined route. We need to track the location of vehicles and raise some kind of alert if they leave their route. So let's take a look at how we might architect the backend for a system like this. So each one of these boxes represents an X application. We're not really thinking too much about like how it's deployed or anything like that. So over here we've got our vehicles out in the wild, driving around, reporting in GPS coordinates, speed, maybe a vehicle ID or something like that. The vehicle event gateway just takes those messages and converts them into that efficient internal binary format that we then pass on to the vehicle event processor. The vehicle event processor takes all of those messages coming in from the vehicles and basically runs that business logic to say, is this vehicle still within its route? And to do that, it sort of checks its in-memory reference data. And that reference data is sourced from the master. So over here, we've got an admin who's like, sitting there when they buy a truck or change routes or whatever, he'll use some sort of web UI or something to send commands to master to say, hey, we've got this new vehicle, we need this vehicle to follow this route, etc., etc. And the master is just like, creating Java objects that sort of models that state and linking it up to X to take care of the underlying replication and HA concerns. So the vehicle event processor is sort of reaching out to the master for that reference data, and it has its own in-memory representation of the state that it needs, which is sort of an amalgam of what's in the vehicle master's state and the data that's being reported in by the vehicles. So it can use that state to determine, okay, well, this vehicle was last at this position, but it's now gone outside of its route. When something does go wrong, like a vehicle going outside of its route, it'll send an alert to the vehicle alert receiver, and the receiver's job is basically just to raise the alarm to sort of page somebody or send a text message or something like that. You might also be wondering why we have, why we've split this up into 4 applications. The idea is basically these, there's different scaling concerns here. So this flow here, like where we're going from vehicles through the gateway to the vehicle event processor, we'll be seeing, probably orders of magnitude more traffic than the vehicle master or the vehicle alert receiver. So these can all be scaled independently of one another. Okay, so if we were to build our fleet management system from scratch today, we'd take this approach. So we'd model out the application state, sort of all our domain objects, I guess. Model the message schema that applications need to use to communicate with one another. So when the vehicle event processor needs to send a message to the vehicle alert receiver to say, hey, this vehicle has gone outside its route, we need to define the message that we send, to the receiver. You write your business logic in message handlers, which you've already seen a few times, I think, today, and then we're ready to deploy and run. Okay, so that's pretty much it for the slides. So let's jump over to look at some source code. Okay. So before I was saying that we sort of look at, we start by modeling out the state, then we move on to modeling messages and write out business logic. So this is the XML that we write to model out our state objects. So you'll see here we've got this repository, and the repository is made up of a collection of vehicles, maps from string to vehicle objects. You don't have to worry too much about those details, but do remember that we've got this repository state object. Over here, these are the messages that are used to communicate with the vehicle event processor. So the location event message is that efficient internal representation of the vehicle event that's being sent to us from, like a physical vehicle. So we've got a vehicle ID, a timestamp, location, and speed. If something goes wrong, we want to send a route violation event to the vehicle alert receiver. And that includes, sort of similar information about what's going on. So over in the vehicle event processor, you'll recall that we just looked at this location event message in messages.xml. So basically, location event message is just a POJO, and we're generating a Java class from this messages.xml. Likewise, we've got the repository, our state object, which is a Java code generated from this state.xml. So this is the handler that's sort of taking care of all of those messages, those location event messages coming in from the gateway application, and this is all of the business logic that we're applying to that message, and we're modifying our in-memory state here. So we've got our event handler annotation up here to let X know that this is an event handler method, and X will use the fact that you've declared this as an event handler and the type of this message to determine, okay, well, this is the event handler for the location event message that we need to call. So as for the actual business logic itself, it's I don't want to get too much into the weeds, because this is really like application centric. Like for your own code, it would probably look completely different. Basically, we do some quick validation. We get the route associated with the vehicle ID on the message that's coming in. We look up our own representation of that vehicle, and we basically check to see if it's still in its route boundary. And if it is, we update its state and don't raise the alarm. But if it's outside of its route, then we want to send an alert through to the alert receiver. So you'll see here we're creating a route violation event, calling a bunch of setters on it. Then down here we actually send it. One thing you might notice is we've got this create method over here. Under the hood, we can pull objects for you. So you can configure X to actually pull the message objects that you create. And that lets you sort of achieve that sort of zero garbage configuration if you really want it. So that's pretty much all there is to the actual event handler itself. I think the important takeaway is probably these couple of lines here and these lines here where we're sending a message. Everything else in here is sort of up to you. Like that's your logic. That's what your application needs to do. So I guess one last thing in the code. Once we've sent a message, it might be interesting to see how how that message is received and processed. Let's increase the font size a bit there. So basically over here you'll see we've got this route violation event. We're calling message sender send message and sending that event. And through all of X's configuration, it determines, okay, we need to send that through to the vehicle alert receiver, and the receiver itself has this event handler that takes care of handling route violation events. And the implementation of this method is like a stub. We're not actually paging colon or anything like that. We're just sort of incrementing a counter and recording some latency stats. A real implementation would look a little bit different. But hopefully you can see the connection between, okay, we've got our vehicle event processor where we're sending this route violation event message, and the vehicle alert receiver where we're receiving that message and doing stuff with it. Okay, and that's just about it. I'm going to open up our demo. I sort of kicked this off before we started the presentation. So here we've got our vehicle event processor processing, what's that, 114K messages a second, maybe. And what's interesting is it's doing this with a single thread. Like the message handler itself is just one thread. The formatting here is a bit funky. You'll have to ignore the gaps over here. It's just aggregation issues, I think. Over here you can see our response times. The median is sort of between 4 and 6 microseconds, and these spikes look kind of scary, but that's 150 microseconds that we're doing there, and we haven't really sort of sat down and tried to hammer out those long tails and figure out the details of why do we have these spikes. But you can see that even for something that we've really just sort of thrown into our performance lab, it performs really well, and we're doing plenty of throughput, especially considering how few we've only dedicated one message handling thread to processing these messages. Yeah, so I'll leave this running, but I think we're probably on to questions now. Lynn and Helen?
Great, Tom. Thank you. We do have a couple of questions, and just to remind anyone, if they have some questions, if they will post those, we will address those shortly. So, Tom, are there any particular performance or data size requirements that would tell me when I should use the X platform?
Well, I'm not sure. It's a case of waiting until you have sort of specific needs around performance or throughput or anything like that. The idea is it should be almost as easy to write the low throughput system that's deployed to a single JVM as it is to write the high throughput system that spans multiple machines. And that's basically because X itself takes care of most of the heavy lifting under the hood. Again, you really should just be able to write those message handlers, the business logic, and X should take care of the rest for you. And then on top of that, from day one, you get HA if you want it. You get guaranteed delivery if you want it. Sub-millisecond response times, all that sort of stuff. Yeah, I think I've sort of touched on it in passing, but with some careful planning, your business logic doesn't even necessarily need to change as you scale up. You sort of just say, okay, throughput has doubled overnight, let's add another message handling thread, and everything else is taken care of by X. So I guess the point I'm trying to make is that if you start with X for the simple stuff, it's easy to do so, but you get a number of benefits from day one on top of that. But then, as you go, you get familiar with the way that X does things, and later it's easy to scale up when you need to do that. Yeah, hopefully that answers the question.
Great, thank you, Tom. And Colin, we have another question. Can we use your product as a replacement for Kafka? And if no, do you provide a messaging bus? And then how does your product compare to Kafka? So kind of a three-part question there.
Okay, let me see if I can unpack that. So I think the first part was, can you use our product as a replacement for Kafka? Yes, I think is the answer to that. We're similar to Kafka in that Kafka is also sort of a stream processing platform. So X is similar to Kafka in that we do stream processing very well as well. I think one of the differences is that we can do exactly once delivery, so completely lossless messaging, whereas with Kafka you have to deal with the possibility for duplicates. But at the same time, we also can integrate with Kafka. We can use Kafka as a messaging bus. Tom touched on it briefly, but if you noticed looking at the code samples that he showed you, there was no sort of messaging provider specific code calls. So the platform works by allowing you to plug into any messaging provider that supports guaranteed messaging. So as Kafka can act as a messaging bus, we can actually use Kafka underneath the covers as a message broker. The difference is you'd be writing your event handlers in X using sort of the simple APIs that Tom talked about. So let me see. Did I answer all the questions there? There were 3 parts, I feel like. Yeah, I think I covered it there.
I think you got it. All right. Well, if we don't have any further questions, if you do, we'll quickly post them and we'll get to them. If not, Tom, great job, and we enjoyed you being here. Please remember that we will post the recording hopefully tomorrow so that you can go back and re-listen to it if you need to, and please give us a call or an email and let us know how we can help you. Thank you for joining us today, and we appreciate your time.
Well, thanks, Helen.